Good morning, dear students. So let's have a topic on exponential and logarithmic functions. So basically, the students for high school they need these concepts of logarithmic functions and especially exponential because you have so many applications and so many involvement of logarithmic functions in calculus, in trigonometry, in functions. So you need. So I thought about to give you an idea of the logarithmic functions. So first of all, I will explain exponential functions. So exponential function is defined by fx equal to b to the power x, where b is positive and b not equal to 1 is called an exponential function. B is called the base and x is called the exponent. So this type of functions are called exponential functions. B can be any number more than 0, 2, 3, etc. And the domain of f is the set of real numbers. So you can check the graph. Yeah, this is the graph. This is the exponential function, increasing function, and something to the power 0 is 1. So that is why it cut the graph cuts the y-axis at 1. So look at that, it's increasing and no part in the negative y direction. So it's always positive and it is increasing. Fx equal to 2 to the power x, and fx is equal to 1 by 2 to the power x is decreasing. So it's like this, the second part, and it's symmetric. It's beautiful graph, it's symmetric. We usually say that exponentially growing. Okay, this type. So exponential function is an increasing function. Now the exponential function with base 2 is the function fx equal to 2 to the power x. The domain is, as said, it's real number to real number, minus infinity to infinity, because you see if this is your x-axis, so this is your domain. Okay, this is your domain. So you can easily find the value of f3, 3 by 2, whatever, f0, 1. So that is why it cuts the graph at 1, y-axis at 1. Now if the value of fx is related for values of x follows -1, it will be half, -2 by 3. It's also give you the number. So any number between minus infinity to infinity, you will get a value of fx. Now there are some laws of exponents. You might have a knowledge of that, but let's have a recap. B to the power x times b to the power y, that will be equal to b to the power x plus y. B to the power x by b to the power y, that will be equal to b to the power x minus y. B to the power x whole to the power y, that will be b to the power x y. AB whole to the power x, that will be a to the power x, b to the power x. A by b whole to the power x equal to a to the power x by b to the power x. So okay, so these are the few laws on exponents. Now let's have an example. Let fx is equal to 2 to the power 2x minus 1. Find the value of x for which fx is equal to 16. So we want to solve this. So 16 you can write 2 to the power 4. You know, if a to the power x equal to a to the power y, then we know that x equal to y. So we can write 2x minus 1 equal to 4. From that you can get the value of x. That's very simple, very easy. More example you can go on. Domain of the real numbers. Sketch the graph of 2 to the power x. Already I've shown the graph. This will be the graph. You see, this is the exponential function, and this is the point 1, because 2 to the power 0 is 1. So y-intercept is 1. Okay, and look at that. This is exponentially increasing. So your domain is minus infinity to infinity, but your range, what is the range? The range is 0 to infinity. Look at that. The vertical stretch is from 0 to infinity. Strict inequality. 0 to infinity is the range. And there is a table of values. You can calculate the table of values. These values will be needed to find out the graph. And this is the last line you see. Its range is 0 to infinity. That I have explained. And this is the graph. Sketch of the graph. Okay, you can draw any exponential graph like this, 3 to the power x, 5 to the power x, e to the power x also. I will explain e to the power x, and sketch the graph of the exponential function, that is half to the power x or 2 to the power minus x, that is negative exponential function. So negative exponential function will be decreasing, as I have shown you. Yeah, this is the decreasing function. You look at that. It's a symmetric. If you dot together, that is 2 to the power x and 2 to the power minus x, that will be a beautiful symmetric graph. Okay, one is a increasing, one is a decreasing. So look at that symmetry between the two functions. Now these are all properties of exponential function, so already explained. Now the base e. The exponential function to the base e is an irrational number, that is sometimes called Euler number, and whose value is 2.718, etc. It is an irrational number, play an important role in both theoretical and applied problems. And it can be proved that e is equal to limit m goes to infinity 1 plus 1 by m whole to the power m. That this limiting value will be e. So e is an irrational number, and the base can be exponential function, the base can be e, and e sometimes called an Euler number. Okay, so e to the power x, so e to the power x is similar to exponential functions, other exponential functions, and you can check the values of exponential functions e to the power x in the table. You can check the values at the table, and you can use these values to draw the diagram. So this is your diagram. Look at that. This is the exponential e to the power x diagram, and naturally e to the power minus x will be like this. Okay, this is your e to the power minus x decreasing, and exponential e to the power x is increasing. So we have talked about e to the power x also. Now e to the power minus x, you can check the table for e to the power minus x and draw the graph of e to the power minus x. Okay, this is your e to the power minus x graph. So that's all about exponential function. So let's talk about logarithmic function, the main important thing, why I have talking about the basis and why I have talked about the exponential function, because of this logarithmic function. Actually, logarithmic function is the inverse function of exponential function. That is the thing. So yeah, suppose y equal to, forget about y, let a to the power x equal to m. Suppose this is the thing. So in that case, x equal to log m base a. That is the definition of log, actually. Okay, that is the definition of log. So if a to the power x is m, if a to the power x is m, then x equal to log m base a. So that is the logarithm. That means you are solving for x. You are solving for x. So you need x. This is the exponential function. You need x. So this is the definition of log. And this base can be of different types. Base can be 10 or base can be e. This is called common logarithm. This is called natural logarithm. Base can be 10 or base can be e, or base can be any other number, no problem. But there are two types of logarithm. One is a common logarithm, another one is a natural logarithm. So this is the definition of log. If you want to define for x, if you want to find the values for x, solving for x, this is the definition. If a to the power x is m, then x equal to log m base a. That is the definition. Base is base, but you have a value, and you have a log table also. Okay, so look at that. What is the is solve for x? That's a simple problem. Log x base 3 equal to 4. Then what is your x? X is equal to 3 to the power 4. So your base is base always. Okay, or you want to write in a reverse order. So what you can write? Log x base 3 equal to 4. That's it. You can go this way or you can come from the this way. You can come from exponential function to logarithm. You can switch to logarithm to exponential function, both ways, because a logarithm function is an inverse function of exponential function. More examples. Suppose solve for log 416, 4 base 16 equal to x. For x, you have to solve for x. So you can write 416 to the power x, that is 4 to the power 2x. So x 2x exponential function. So 2x equal to 1, x equal to half. Very simple. Okay. And let's solve for log 8. Simple solve. This is very simple. Log 8 base x equal to 3. So base, what you can write from the definition? Recall the definition. If a to the power x is m log m base a equal to x. Okay, so if a to the power, or you can go if log m base a equal to x, then a to the power x is m. So x cubed is 8, right? And 8 is 2 cubed. So x equal to 2. That's it. Okay, that is the exponential properties I am using. So this is how you can deal with the problems. Okay. Now, as I talked earlier, that uh, base 10, then that is for common logarithm, base e, that is for natural logarithm. So two types of, you can write ln x also, and common logarithm you can write log x. Now there are some properties. Laws. If mn and n positive numbers, then log mn base b is equal to log m base b plus log n base b. So if there is a product of two numbers, then log can be split into two sum. And if there is a division, then it can be your minus. Then that can be equal to the difference of logarithms. And if there is a power, then power n log m base a. And if the log 1, that will be 0, and log b base b, that will be 1. So I will prove 1 for everybody how these results came. So let me show you. Yeah, let log, what do you have, m base b. So let m base b equal to x. Okay, then your b to the power x equal to m, right? And log n base b, sorry, let me write log n base b equal to y. Then from properties of log or definition of log, b to the power y equal to n. Clear? So I'm supposing log m base b is as x, that implies b to the power x is m, and log n base b as y, that is b to the power y is n. So a to the power x into it's b to the power x. Okay, that is b to the power x into b to the power y equal to mn, right? And b to the power x plus y equal to mn. Got it? Now from here, using the definition of log, you can write log mn base b, sorry, let me add a page. So I'm proving the things so that you understand the logic, or it will be easier for you to apply those problems. Okay, that is my target actually. Okay, That's it. So b to the power x plus y is mn. So I'm using the definition of log x plus y is equal to log mn base b. And what is your x? X is log m base b. What is your y? Log m base n base b. Yeah, that's it. Equal to log mn base b. That is the proof. It's very simple. That is the proof of the one. Okay, that is the proof of that. So I'm assuming log m base b as x. So that implies b to the power x as m. Log n base b as y, b to the power y is n. So you are multiplying, so you have b to the power x plus y as mn, and using the definition of log x plus y equal to log mn base b, and x is nothing but your log m plus m base b, and y is log m n base b. So you have this property 1. Similarly, for log b number 2, you can take b to the power x by b to the power y. In this case, you can x b to the power x by b to the power y. So you will have b to the power x minus y, and simple, very simple case. Okay. And what about 4? 4 is also very simple, because you see b to the power 0 is 1. Something to the power 0 is 1. Now using the definition, log 1 base b is 0. And b to the power 1 is b actually. So using the definition of log b base b is 1. Whatever be the base, log 1 is 0, whatever be the base. And if your base and log and upper one is same, it will be 1. So these are the properties, and this is the power. You can prove similarly using this logic that I have used to prove 1. So log m to the power n base b is n log m base b. So your power comes forward. So multiply the logarithm. So that is why, that is how. Now I will explain one more, the base change properties. That is very important. How will you base change your base? Okay, that is very important. Let me show you. Okay, I'm writing base change. Changing of base is very important. So let me show you. Log, suppose you have log m base a and you want b base. So I'm writing log m base b times log b base a. Okay, look at that. I have changed the logarithm base of the logarithm to b. So this is called base change law or base change property. That is very useful. That is very useful. So if I write m equal to a, then this is your 1. If I write from here, we can write another thing. This is the base change property. So if you want e base, suppose if you want e base, log m base e is equal to, if you want e base, sorry, not here, in any intermediate stage, if you want e base, then log m base e equal to log e base a. So that's the use of the change of base property, change of base change properties. Okay. Now suppose if you write m equal to a, let us write m equal to a, then it will be log a base a, that is equal to 1 on the left, and you have 1 base, yeah, you have 1 base b. So you can write also, what I want to say, you can write also log a base b equal to 1 by log b base a. Okay, that you can write. It's just switch over the base and the main logarithm function. Okay, that is the use, that is the main base change properties. Okay, so this is very important. Base change, changing base is required in everywhere. Suppose you are doing some problems on calculus, limits, functions, you need to change that base. Let's have an example how you are using. You see the given log 2 is 0.3010. These are all from log table. You can find out in your calculator also. This is common logarithm value, that is the base is 10, log 3 is 0.4771, and log 5 is approximately 0.6990. So how will you calculate the log 15? You see log 15, you can write log 3 into 5. So log 3 plus log 5, you substitute the values, you will get the answer. So this is the use of the logarithm. You can use the logarithmic table also. You can use your calculator for calculating common logarithm values. So this is the calculation. So log is a operator. Log is an operator, used as an operator. It can operate on number functions, and you can use it as a tool, mathematical tool. Also, again, find log 7 in 0.5, it's 15 by 2. So I'm using 3 into 5 by 2. You know, log division of log is subtraction. So you can write using the laws of log here and substitute the value, you get the values. More examples, suppose I want to calculate log 81. So log 3 to the power 4. So this is the power property laws. So power comes forward, 4 log 3, and that is approximately this. You know the values of log 3. So log 2, log 3, log 5. These three are the basic values actually. Log 50 similarly, again I'm log 5 into 10 and log 10 base 10. This, if nothing is written in the base, that means it's a log 10 base 10, that is 1. So you can write log 10 base 10 as 1. Okay, so you get the values. Suppose log x square y cube base 3, it can be written as log x square base 3, log y cube base 3. So 2 log x, 3 log y. Okay, that is how. Changing, using the base, using the laws of logarithm. More simplification, log x square plus 1 by 2 to the power x base 2. So this is a division. You can write subtraction, you can split the log and write subtraction, log x square plus 1 minus log 2 to the power x. Again, it's x is the power, so you can write x times log 2 base 2. Log 2 base 2 is 1. You know that's base and the log is same, then that will be 1. So log x square plus 1 base 2 minus x. So that is the use of laws to simplify the results. And if you have any complicated form, suppose you have x square plus 1 by 2x cube root, and that is equal to y. So you want to simplify this. This can be simplified easily or very beautifully by using log. How? Take log on both sides, and this is the power, cube root. So cube root times log of x square plus 1 by 2x. Look at that, it's simplified. Root can be easily simplified, and further we can simplify it. Log of x square plus 1 minus 1/3 log 2x. That is how we have simplified. Okay, so this is very complicated result, but very complicated expression in function can be simplified using log. Look at that. This is ln. Ln means e base you have. So you have this already taken log, of this. So you can simplify using this. Look at that. Log x squared, this log multiplication, addition, division is the subtraction, and e to the power x, x is the power. So x log e, ln e. So e base e is 1, ln e is 1. So this is the simplified result. So a lot of simplification have been done. So you can solve the using the log. There are so many problems using log, solving logs. So x plus 1 minus this. So you can write x plus using law 2, x plus 1 by x minus 1 equal to 1. And that is using definition of logarithm. 3 to the power 1, this should be equal to, and it is very simple to calculate that x equal to 2. That will give you x equal to 2. More examples we have. This is very simple. Look at that, very simple properties on log. And there is a mixture of APGP problems also. By solving this type of things, you can solve this. Okay, so this is how you can use your properties of logarithm and laws to solve the values for x. Okay, and logarithm of function fx, you can write log x base b. You already know the domain will be, yeah, let me draw the diagram for you. So domain will be all positive numbers. If you write fx equal to log x base b, domain will be all positive numbers, because log negative is undefined. You cannot define log, because b is positive, b not equal to 1, and x cannot be negative. X cannot be negative, x is always positive, x cannot be 0 also. Let me show you the diagram. So domain is 0 to infinity and range is minus infinity to infinity. The graph passes through the point 1 0, and it is increasing for b greater than 1, decreasing for b less than 1. That's very important. Yeah, you see, if you draw y equal to e to the power x, and if you draw y equal to x, log x is the mirror image of the exponential function. Log x, graph of log x is the mirror image of exponential function. Look at that. This is the log x. You look at that, this is the log x, and it cuts the x-axis at 1, x intersect 1, 1 0 is the point, and it's increasing, and there is no negative branch on the left of 0. There is no branch of log x. So log x is an increasing function for b greater than 1. If the base is greater than 1, it will be increasing. It will be increasing. Let me show you in a graph again. Yeah, yeah, that's it. That's it. So if you draw the diagram, yeah, so you see this is your logarithmic function. This is suppose 1 0. So it is increasing. It is increasing for log x base b. B is a base. Base is more than 1, then it is increasing. If the base is less than 1, if the base is less than 1, then it is decreasing, and it will be like this, symmetric. If the base is less than 1, base is less than 1, and look at that, left of 0 there is no branch. On the left of 0 there is no branch of log x. So 0, at 0 you can't find any branch. So at 0 log is undefined. For negative values of x, log is undefined. Only for positive, x greater than 0. So that is the domain. So domain is 0 to infinity. Look at that, your domain is 0 to infinity. And what about the range? You see, the range is minus infinity to infinity. The vertical stretch is minus infinity to infinity. Okay, minus infinity to infinity is the range of log x. And remember always that for b greater than 1, more than 1, log x is increasing, and if the base is less than 1, log x is decreasing. That's it. Okay, yeah, and there are some more problems. So these are very easy, exponential. And I'm not explaining this. There are some applications. I will just mentioning those. Growth of a bacteria, radioactive decay, assembly time. These are the actual applications of exponential functions and mathematical models. You can form a mathematical model. Suppose in a growth of a bacteria, how will you explain? In a laboratory, the number of bacteria in a culture grows according to qt. T is a time, q is a function of t, q naught e to the power kt, k is a constant. So this is the mathematical model for growth of a bacteria. You can explain. And exponential functions are increasing. You know, this COVID-19 situations, sometimes the this virus was exponentially increasing. A lot of people are infected throughout the globe. So this is exponential growth that can be explained also mathematical model. There must be some mathematical model. So this is the one of the mathematical model to explain growth of a bacteria. So you can calculate everything. You can calculate the using log also. You see the log applications here. if you know the at t equal to 2, the 60,000 bacteria, what will be the exponential function, logarithmic function, what will be the value of k, number of bacteria present at any time t, you can calculate. So everything can be calculated. Okay, so these are the applied problems. And for radioactive decay, similarly, you can explain the radioactive decay qt. In this case, you have e to the minus kt. Half life, you know, the radioactivity, half life of a radioactivity is the time required for a given amount to be reduced by one half. So half life of a radium is approximately 1600 years. So you can calculate everything. So if you have a data, if you have a mathematical model, you can calculate everything. So that's all for today, everybody. So I have explained, uh, try to explain very easily for you so that you can understand the exponential functions, especially logarithmic functions, because a lot of students require logarithm functions for calculus in 12 in boards, and also JE for some applications, but logarithms is not in your chapter in your book. So I thought logarithmic functions, the graphs and the applications, you need this. And go through the video. Please subscribe and you share my videos.